Okay, let's talk about gases and kinetic molecular theory. So our goal is going to be to figure out how to use the math so that we can talk about kinetic molecular theory, and that'll involve calculations with pressure, volume, temperature, and moles of gas. So remember that there are three different states of matter: solid, liquid, and gas. We're going to focus on gas, but many of the things we're going to talk about can be applied to solids and liquids as well. So thinking about gases, we know that they consist of tiny particles, atoms or molecules, and the particles are in constant random motion. They're colliding with the walls of the container, and this is what causes pressure in the container. Let's take a look at your PhET simulation just a minute. Remember this? Let's start over. Now, look at the pressure gauge. It's 0. As soon as I add some gas to the container, oh, look, it didn't register bigger than 0 until the molecules started bumping into the sides of the container. Look at that. It goes up just a little bit as they start bumping around a little more. So it's these collisions with the sides of the container that cause gas pressure. Another assumption that we're going to make is that the volume of the gas that we measure is made up by the distance between the particles and not the particles themselves. Atoms and molecules are so small that we assume their volume to be negligible. The particles are assumed not to attract or repel each other as well, that the collisions that they're forming are completely elastic. And so these guys are not moving very fast. Let me see if I can get them heated up and moving a little bit faster, and watch them bounce into each other. They don't stick to the walls and they don't stick to each other. That's what we mean by inelastic collisions. And the last assumption is about their average kinetic energy, that it's directly proportional to the Kelvin temperature in degrees. So if you look back at what I just did when I added the heat, the fire out of the bucket, and I raised the temperature, notice it's being measured in Kelvin. That's what sped up the little particles. So what is that relationship between kinetic energy and velocity? Well, remember from physical science or maybe physics class, you learned the equation for kinetic energy is 1/2 mass times the velocity squared. You know the mass of the little particles aren't changing. So what's going to increase their kinetic energy is the velocity. If we look back over here at our little simulation, we've kind of maxed out that temperature. Let's go the other way. What if I decrease the temperature? So I'll put it on ice. And you can see as kelvins decrease, these guys start to slow down a little bit more. Okay. I'll go ahead and slow them way down. Do you see, can you visually see that their velocity is decreasing? Okay. We can actually look at this a different way. We can measure the speed of our particles. And if I put some of them in there and I look at the speed, now look at your graph here. The number of particles is on the y-axis, and then the speed at which they're moving. So this bar graph here is showing you how many of each of the particles are moving their particular speed. So we can see right now, not very many of them are moving at fast speeds. We'd have bars out here if we had particles that were moving very quickly. But if we increase the speed, we can see that we get an increase in the number of particles that are moving at a higher speed, a higher velocity. Okay, and if I continue to apply that heat, you can see the number of particles doesn't decrease, so it kind of spreads out. Now we have them moving at all different speeds. The important thing to realize, though, are they all traveling at the same speed? You can kind of see that visually, and your graph is really telling you that. If we plot kinetic energy, the same thing. They're not all moving at the same speed. So it's the average speed that we're measuring when we measure their temperature. Okay, so temperature is a measure of the average kinetic energy, and we use the Kelvin scale for this reason, because look over here. Celsius is 0, way, way up here. And we know when particles are frozen that they still have some energy. It's not until we get over here to the Kelvin scale and go all the way down and stop those particles in their tracks that we get to 0 kinetic energy. So it's not really useful to base everything on water. We have to base it on absolute energy. So a lot of our calculations we're going to do based on Kelvin. Even less useful is the Fahrenheit scale when it comes to looking at the energy of particles, because the Fahrenheit scale is based on something that's not even really the freezing point of water. It's at 32. So absolute 0 is 0 Kelvin. The Celsius scale really isn't sufficient. Well, how do we convert between the two? Because most of the measurements we're taking are going to be in Celsius. To go from Celsius to Kelvin, you're going to add 273. And then if you're in Kelvin and you want to go back to Celsius, you'll just subtract. There is a formula for Fahrenheit, but we're not going to worry about that right now because that's difficult. And if we just take our measurements in Celsius or Kelvin, it'll make it a lot easier. Now, one other thing that I did want to point out to you, and I'm going to do it on this screen, is the fact that a Kelvin degree and a Celsius degree are the same size, okay? Look over here at this. If I start at 0 degrees Celsius, and let's say I heat up my ice and I go to 10 degrees, I've made a jump of 10 degrees. Come over here. What if I measured it at 273 and I heated it up 10 degrees? It goes to 283. Those are the same size. Now, if I look over here at Fahrenheit, from 0 to 100, from freezing to boiling, there's 100 degrees in there. But if I go from freezing to boiling on the Fahrenheit scale, that's almost 200 degrees in there. So a Celsius degree is quite a bit bigger, almost twice as big as a Fahrenheit degree. Okay. I've got a couple of practice problems for you to do, and I'll let you do those, and we'll come back and we'll look at their answers. Okay, good job on converting. Now let's look at how do we measure those particles of gas. So how do we measure the molar volume? Remember, molar is the number of particles in a gas. 1 mole, 6.02 times 10 to the 23rd, represents 1 mole of gas. Remember this guy, Avogadro? He actually was studying gases when he came up with his idea about the chemical mole. And he discovered that gases, when you had the same amounts, they always occupied the same volume, regardless of the type of gas it was. And so really his first law that he came up with was this idea that if the gases were at STP, STP stands for standard temperature and pressure, which just happens to be 273 Kelvin, that's 0 degrees Celsius, and 1 atmosphere. The volume is always going to be 22.4 liters, regardless of the gas you have. So we call that the molar volume of gas. Would you be able to calculate the number of moles of helium that are contained in a 1 liter balloon if it was at STP? Remember, 1 mole contains 22.4 liters. Good. Here's another thing for you to think about. What if we wanted to convert an amount of gas to moles? We would use 22.4 liters. Here's a problem for you to think about. How many liters of oxygen gas are required to combust 1 liter of methane gas, that's CH4, at STP? So the first thing that you're going to have to do is convert your liters to moles. Then you can write the balanced equation and use the mole ratios to solve for the number of moles that would be formed. Then convert your final units in the specified problem for non-STP conversions. Let's look at an example of that. Okay, I have these weird things on my... Okay, so the first thing that we need to solve this problem is to analyze what they're asking us. How many liters of oxygen are required to combust 1 liter of methane gas? So just like if it asked us about 1 gram of methane gas, we can't do anything in liters. We need to convert to moles. So how would we convert 1 liter to moles? So we know that the reaction is taking place at STP. We know that there are 22.4 liters per mole at STP. So if I have 1 liter of CH4 and I multiply that by 1 mole per 22.4 liters, I stick that into the calculator, I'm going to get, why is it not typing? Boink. I'm going to get an answer of 0.45 moles. Okay, so now I know the number of moles that I'm wanting to react. What's the next thing I'm going to need? Just what we always need, a balanced equation. So the next thing you're going to need to do is write a balanced equation for this reaction. So remember that anytime you combust something, you add oxygen, and your product is always going to be CO2 and water. So now we need to balance. So by adding a 2 to the oxygen and a 2 to the H2O, we should have a balanced equation. All right. The next thing we're going to need to do is look at the mole ratios and figure out how many moles of one thing produce another thing. So they want to know how many liters of oxygen gas are required. So right here is our oxygen. It takes 2 moles of oxygen to combust every 1 mole of CH4. So if we set up our mole ratio equation, we know that we have 0.045 moles of CH4. I'm sorry, I'm not doing the subscript on that for you. And our ratio of methane to oxygen, we have 2 moles of O2 required for every 1 mole of CH4. How about if I do this a little bit nicer? Okay. And so if you put that in the calculator, you know that we're going to end up with 0. Oh, whoops, it's not typing again. I'm sorry, guys. 0.09 moles, and that's going to be moles of O2. Run out of room there. Okay, if I do it this way, it'll make a little more sense. So now I know how many moles of oxygen gas are required. Okay, make this a little bit prettier. But the question did not ask me for moles of oxygen. They want to know how many liters of oxygen. So now I just need to go through that same exercise as before. I have 0.09 moles. I know that this is occurring at STP. Now, that's a little bit of a stretch of the imagination, because if it's on fire, it's probably not going to stay at the same temperature. But for now, that's what the problem says, so that's what we're going to do, and that makes it a lot easier. So 0.9 moles of, and this is of oxygen, okay, and we know that for every 1 mole of oxygen, we're going to get 22.4 liters of gas. So we get 22.4 liters for every 1 mole. That way, moles on top, moles on bottom, they're going to cancel out. And that'll give us 2.016 again, it is not typing, 2.016 liters. And we were looking for oxygen, and that's going to be O2. All right, so how is this different from other stoichiometry we've done? The only thing that we're doing different is instead of converting to grams from moles, is we're converting to the liters or to a volume from moles. So you still have to work in moles, but you're just going to convert to liters instead, and your magic number is 22.4. This is a lot easier than doing mass, because with mass, every compound is different, so you have to calculate a different molar mass. With volume, it's always going to be 22.4. Don't forget, though, you have to have that magic STP. I'll show you a little bit later what we'll do if it's not at STP, but for now, we've got the easy problems. Okay, let's review just really quickly how we measure pressure. We're not going to do a ton of, we're not going to do any of these calculations, but it's probably prudent to remember where this idea of pressure comes from. So pressure is just force over area. So how much force is being applied over a particular area. It's in Newton meters squared is how pressure is calculated, but we give it its own unit called a Pascal. And Pascals are really small, so usually we're going to be measuring in kilopascals because we are usually measuring significant amounts of pressure. So which activities in the gas properties lab show direct evidence that we even have air pressure all around us? So you guys did a really awesome job on that lab. I hope I haven't embarrassed anyone, but if you were in class, I would have made you do this in front of everybody anyway. So the card on the glass, remember, the reason the card didn't fall off isn't because it was being sucked up or stuck. It was because of air pressure pushing the card up, and it pushes up on the card more than gravity pulls down on the water. Over here, you couldn't suck up with one straw in and one straw out because you could never create less pressure in your mouth than in the atmosphere outside. Atmospheric pressure was rushing in, so the water didn't know any difference and it wasn't going to go into your mouth. This is kind of hard to see. This is the best picture that was made, and so I think Hannah Glass, you're the one that got the best picture. But you'll see that the spout on top is not near as big as the spout on bottom because there's more air pressure pushing down on the top, and it only flows when the cap is open and exposed to external air pressure. If you close that cap off, most of the water is going to stay inside. The candle, the water was sucked up into the candle because when the flame burned, it used up some of the oxygen, and the volume inside and the pressure inside had gone down, and that caused a vacuum and the water got sucked up inside. This is a fun one. I only saw one person do a submission on the shrink rack being a person, but the reason you get so tied up in that garbage bag is because when you take the air out, the pressure is unequal and it's all pushed around. The air pressure is pushed all around that bag, and then you can't move. It's really fun. If you didn't get to do that one, try to find time to do it because it's a lot of fun. And then this one, let's see if I can get it to run. The crush the can. Get my head out of the way there. That one's great. Good job, Abby. That was a good video. So the gas on the inside of the can shrunk, which caused a shrinkage in air pressure on the inside of the can. Pressure's greater on the outside. The can gets crushed. And there's one more that I thought was great. This is Abby again. You can tell she's a TV pro or a video pro. But this is the one with the egg in the bottle. And so we put the match on the inside, and again, the match is evacuating.
Oh my gosh, it's doing it!
It's pulling the pressure down, and because the pressure decreases on the inside, air pressure, is pushing the egg into the bottle. Now their egg kind of gets a little bit mutilated there, but it was fun to watch anyway. Good job, guys. I really enjoyed everybody's video submissions and picture submissions that you did. All right, let's zoom back over here and get going with this. It's getting kind of long. So what is atmospheric pressure? We just talked about force over area is pressure, but think about all of the gas all the way up like 14 miles up in the atmosphere. All that air is being pulled down by gravity, and that's going to push on you with quite a bit of force. So that's what we mean when we talk about atmospheric pressure. And as you're going through your experiments and looking at different phenomena that are happening in chemistry or physics, you have to remember that air pressure is always all around us. Let's see, we already talked about that. Let's kind of liken this idea of air pressure. I'm sure you guys have all been swimming and you have gone down to the bottom of the pool, and you know how your ears feel all poppy and weird down at the very bottom of the pool? Well, that's the same thing that air pressure is doing to us. The more layers that build up on us, the more pressure we're going to feel down at the bottom. One of the ways that we can measure air pressure is using a device called a barometer. And the barometer, so we have air pressure pushing all around on the outside. Originally, it was in a bath of mercury. So the pressure pushes down, and it will push the mercury up into this tube. And when we're at what we call 1 atmosphere of pressure, it will push it 760 millimeters up into the tube. And Evangelista Torricelli, I'm not much into Italian there, he was the one that kind of came up with this idea. And so this unit of pressure is sometimes called a torr. We also call it millimeters of mercury. Maybe you've heard this, like when the weatherman is talking, he'll say so many millimeters of mercury outside. But that's where it came from, was from the old-time barometers that use mercury. We don't really use those now. We use pieces of metal that will expand and contract based on barometric pressure. So there's 3 basic ways that you are going to encounter pressure in this class. And that's going to be in atmospheres, which that's basically what the pressure is at sea level when there's no atmospheric disturbances. kPAs that we just looked at, kilopascals. So 1 atmosphere is approximately equal to 101 kPAs, which is also equal to 760 millimeters of mercury, which is the same thing as a torr. Millimeters of mercury and torr are the same thing. Another idea about standard temperature and pressure is remembering, that STP is 0 degrees Celsius, which is the same thing as 273 Kelvin. And for some of our calculations, you're going to need to convert. Don't use Fahrenheit. There is a way to do it. And if you go to engineering school, they'll teach it to you because Americans still use Fahrenheit. But that's just not right now. We're going to do it the easy way. We're going to use metric. Okay, let's do some practice converting. The local weather conditions report that there's a barometric pressure of 742 millimeters of mercury. Use the information on this page to convert 742 millimeters of mercury to kPa, ATM, good job. So would we say that the current weather is being influenced by high pressure or low pressure? How would you explain your answer? Okay, here's a few practice problems. You've had to listen to a lot, but I'm going to let you do a couple of practice problems and we'll be done for the day. Practice problem 1. You have 5 identical balloons. There they are up above. Pretty colors. Each of them are filled to the same volume, but with different gases. They all are at 1 atmosphere, and they're all at 25 degrees Celsius. Notice not STP. Thinking about what you know about kinetic molecular theory, which balloon contains the greatest mass of gas? Could you explain your answer? Here's another thing to think about these balloons. Same balloons, same conditions. Which balloon contains the particles with the greatest kinetic energy? You might have to rewind the video and look at your kinetic energy equations. Can you explain your answer? Okay, here's a practice problem with stoichiometry. You have your balanced equation up above. 4.60 liters of hydrogen gas at STP reacts with copper 2 oxide, according to the balanced equation above. How many moles of hydrogen react? Good job. Now that you know how many moles of hydrogen react, can you calculate the number of moles of water vapor produced? Did you see a relationship between liters and moles of gas? It's very interesting. Unlike grams, which is different for every compound, because ideal gases all occupy the same volume, you can actually use liters without converting to moles. I know I kind of tricked you on that one, but I wanted you to be able to see that. Here's another one. It's in grams, I know. Equations at the top. 15.5 grams of solid aluminum at STP react with hydrochloric acid according to the balanced equation. How many moles of aluminum react? How many liters of hydrogen are produced? Good job, guys. May the 4th be with you.